Hi, now in today's class we will go through polarity of bonds, right? So in previous video lecture we have understood what is covalent bond, right? And there are types of covalent bonds, right? That we have not done in the previous lecture. So types of covalent bonds are covalent bonds are mainly two types. First is non-polar that we studied in the previous lecture. The other is polar, right? Polar covalent bond. So what do we mean when we talk about polarity? When we talk about polarity, we are talking about charges, right? Positive and negative charges, right? But till the previous video lecture, we took examples of molecules like oxygen, right? Hydrogen, nitrogen, right? And we saw that all these molecules of oxygen, nitrogen, hydrogen does not have any charge separation, right? They do not possess any charges, right? So these types of molecules that do not possess any charges, right? These are known as non-polar molecules, right? And why these are non-polar molecules? If you remember, when bonding takes place between two hydrogen atoms, we have this bond. What does this line represents? This line represents a shared pair of electrons. Similarly, three lines represents three shared pair of electrons, right? We also call it as bond pair, right? So this is nothing but a bond pair or a shared pair of electrons, right? Now there is something called as electronegativity, right? That we have understood or that we have gone through in periodic classification of elements, right? Something known as electronegativity. Electronegativity, right? And what is electronegativity? Electronegativity is ability of an atom to attract the shared pair of electron towards itself, right? Or to displace the shared pair of electron towards itself, right? So this is the attracting power of atoms, right, in covalent bonds. Now if you look at the attracting power of hydrogen atoms in hydrogen molecule, firstly let me just write this is the attracting power or ability to attract the shared pair of electron towards itself, attracting power of atoms in covalent molecule, right? Or we also call it as ability to attract shared pair of electrons or bond pair of electrons, right? Now if we talk about this hydrogen atom, both the hydrogen atoms, right, since they are same atoms, so the ability to attract this shared pair of electrons is same, right, of both these atoms, right? So both these will attract the shared pair of electron towards itself with the same extent, right? The extent to attract this shared pair of electrons by both the hydrogen atoms is same, right? So since the attracting power on the shared pair is same by both the atoms, so this shared pair will lie exactly between, right, these two hydrogen atoms, right? Since this shared pair is between the two atoms, so it's not displaced to any of the combining atoms, right? So both these atoms do not have any charges, right? Because this electron pair is nothing but it's a negative charge, remember, right? And since it is at equal distance from both the hydrogen atoms, so both the hydrogen atoms, I mean they do not have any charge, right, when we are talking about charges. Now let's take example of some other molecule. Let's take example of HCl. Hydrogen atom has one electron, chlorine has 7 electrons. Hydrogen wants to complete 2 electrons. Chlorine wants 8 electrons. So chlorine will share its 1 electron and hydrogen will share 1 electron of chlorine. So there is one shared pair. Now this shared pair belongs to both the atoms, right? So this is how we will draw the molecule, right? Now we have a shared pair of electron, right? Now if we look at the electronegativity of hydrogen and chlorine, the electronegativity, that is ability to attract the shared pair of electron, is more of for chlorine, right? This have high electronegativity, right? Electronegativity of chlorine is high. So what electronegativity represents? The ability to attract the shared pair of electrons. Now this chlorine atom will displace this shared pair towards itself, right? Since I said this shared pair has a negative charge, this is electron pair, so it has a negative charge, we know that. So the molecule, right, which will displace, the atom which will displace this shared pair towards itself will acquire a slight small negative charge, right? And the molecule that is away, right, from this shared pair will acquire a slight positive charge, right? So it will be like this. Due to electronegativity, this is slight negative and this is slight positive. Slight will represent slight negative and positive using delta plus delta minus, right? So till this point we are clear that how charges develop on a molecule that has atoms with different electronegativity, right? Here HCl consists of hydrogen and chlorine, both have different electronegativities. So the atom that has high electronegativity will displace this electron, or will displace this shared pair or bond pair towards itself, thereby acquiring slight negative charge. On the other hand, the other atom will acquire a slight positive charge, thereby developing polarity, right? This is what we call as polar covalent bond, right? This is a polar covalent bond, and the reason for polar covalent bond is electronegativity difference, right? Now we'll be looking into an extreme case, right? Because we know that there is something ionic bond that we have understood, and we know that in ionic bond there is a metal, there is a non-metal, right? Metal has a positive charge, right? Non-metal has a negative charge, right? This has a positive charge, this has a negative charge, right, in electrovalent bond. Now the ability to attract this shared pair will increase, right, with the increasing electronegativity, right? So when the electronegativity will keep increasing of one of the combining atoms, it will displace the shared pair, it will keep displacing this shared pair of electron towards itself, right? And in case the electronegativity difference is too high, right, or the electronegativity of one of the atom is too high, it will displace the electron bond pair towards itself to the extent that the other atom will lose control of its own electron, right? Why we say its own electron? Because this shared pair is nothing but this shared pair belongs to both the combining atoms, we said, right? One electron has come from hydrogen, one electron has come from chlorine, right? So both these form a bond pair or a shared pair, right? Now in one case, when the electronegativity of chlorine, right, goes too high, or any atom, not in case of HCl, if the electronegativity of one of the atom, right, say this, becomes too high, right, or when we say the electronegativity of one of the atom is too high, that means the electronegativity difference between the two atoms is high, right? So when the electronegativity difference is too high, the other atom will lose control of its own electron, and this electron pair will be completely displaced towards the other atom, right, towards the more electronegative atom. Thereby this will acquire a negative charge, this will acquire a positive charge, right? And this is same as your ionic bond, right? So there is, what we say this is, like, there is an ionic character, right, in covalent bond, right? Percentage ionic character in covalent bond, right? So percentage ionic character of covalent bond, right? This depends on electronegativity difference. This depends on the electronegativity difference. Now, if the electronegativity difference goes more than 1.9, then the bond, right, this bond is predominantly ionic, right? And if the electronegativity difference is less than 1.9, then the bond is predominantly covalent. And if the electronegativity difference is equal to 1.9, then the bond is 50% ionic, right, and 50% covalent, right? So this is how you will determine the percentage ionic character based on the difference in electronegativity of the two combining atoms in a covalent molecule, right? So this is important. Now, to determine the percentage ionic character in a covalent bond, there is a formula also, right? The formula is, we call it as, there is an equation to determine the percentage ionic character. To determine the percentage ionic character, there is a formula, or there is an equation, we call it as Hane and Smith equation. Hane and Smith equation. This is your Hane and Smith equation. You may get some problems, some questions in competition exams based on this equation. The equation is Hane and Smith equation. It's 16. Right, plus this is your Hane and Smith equation, right? Hane and Smith equation to determine the percentage ionic character, right? There is another way to determine the percentage ionic character. This is the first way. The second way is your dipole moment. Right, we will do this in some time, right? How to determine the percentage ionic character based on dipole moment, right? So till this point we are clear, right? Till this point now we are clear that how polarity develops, right? Now, if the polarity develops because of the electronegativity difference, and if the electronegativity difference goes beyond 1.9, the bond is more ionic. And if it is less than 1.9, the bond is more covalent. And if it is equal to 1.9, the bond is 50% ionic, 50% covalent, right? So this is how we determine the percentage ionic character. There is a way, we call it as Hane and Smith equation. This is the equation, right? We call it as Xi, this symbol, where this Xa and Xb we can say, or I don't remember the name of this symbol. It's Xi, I think we call. Both these represents the electronegativity of two combining atoms, right? Then there is another way, dipole moment also. We'll look at in a Right. Now let's look into what is the dipole moment. Right. Since polarity gets developed on a molecule, let's say HCl, right? This is a polar covalent molecule, right? It has a positive end and a negative end, right? A positive and a negative end, like two poles, positive and a negative pole, right? So this is a dipole, right? This polar covalent molecule is a dipole that has one positive end and one negative end, right? Since it's a dipole, so it has a dipole moment, right? Dipole moment is due to polarity, right? That gets developed due to electronegativity difference. Now, the charge is same on both the combining atoms, right? But equal and opposite, right? So the dipole moment is calculated mathematically. The dipole moment is product of the charge, right, multiplied by the distance between these two atoms, right? Between these two atoms, right? So charge, right, Q. Dipole moment is represented by nu, right? So charge multiplied by distance between the two atoms in the covalent bond, represented by D, right? So the formula turns out to be this is the formula for dipole moment, right? And the unit in which this is calculated is your Debye, D-E-B-Y-E, right? So just know what is your dipole moment, right? And the unit in which dipole moment is calculated is Debye, right? So be clear with the polarity, right? Because once you understand the polarity, right, you can think of ionic character, right? Because polarity means charges. We know that ionic bond has positive and negative charges, right? Once you understand how polarity develops, you can have an idea that it's a polarity makes one end positive, one end negative. So two poles, positive and negative poles means you have a dipole. Di means two poles, right? Positive and negative pole. So a dipole has a dipole moment, right? The mathematical formula for a dipole moment is charge into distance between the two atoms, right? It's calculated in unit Debye, right? So let's talk now more about dipole moment, right? This dipole moment is how do we represent dipole moment, and then we will see dipole moment of some important molecules, right? Let's just rub this. Dipole moment of some important molecules. We took the example of HCl. Right, where hydrogen has slight positive charge, it has slight negative charge, right? And dipole moment is represented by a dashed arrow like this, by a crossed arrow. You have cross here, and there is an arrow. This arrow points towards the negative pole, and this is your positive. This is your positive pole, and this is your negative pole, right? So if I want to show the dipole moment here, it's like this, right? This is how you show dipole moment from electropositive element towards electronegative element, right? There is a crossed arrow from electropositive element to electronegative element. This is how dipole moment is represented. Right. Now there are certain applications of dipole moment, right? And what basically this arrow represents, this arrow represents the shift of electrons, right? In the dipole moment is represented by this arrow which is pointing towards positive to negative end, and basically this represents the shift of bond pair or low bond pair electrons. Right? This is what it represents, because in polar covalent molecules this bond pair is shifted, right, towards more electronegative atom, right? Since it is shifted towards more electronegative element, the atom. So this is what the dipole moment sign represents. Arrow towards more electronegative means it represents the shift of electron pair towards more electronegative element. Right. Now just let's look into the dipole moment of some polyatomic molecules, right? And the diatomic, in case of this is a simple molecule, so the dipole moment of HCl depends on the dipole moment of one bond, right? Now what about the dipole moment of polyatomic molecules? Right? In case of polyatomic molecules, the dipole moments, right, is due to the dipole moment of individual bonds, right? Let's talk about hydrogen water molecule, right? So dipole moment of polyatomic molecule is due to dipole moment of individual bonds. For example, in case of water molecule, it's like this, right? Since it is represented, the dipole moment is represented from electropositive to electronegative elements, it's like this. Right? This is how it is represented, and the dipole moment of water molecule is due to these two, the dipole moments due to these two bonds, right? And we know that dipole moment is since it has a direction and it has a magnitude, right? We are representing this with a direction, right? So it has a direction and it has a magnitude, so it's a vector quantity. It's a vector quantity, right, that has direction and magnitude. So dipole moment is a vector quantity. So the dipole moment of water molecule is the vector sum of dipole moments of both these OH bonds, right? So net dipole moment is due to the dipole moment of both these molecules, and net dipole moment would be somewhat like this. This is how you will represent it. Net dipole moment would be in this direction, right? Since both are in this direction, so it's in this direction, and the resultant dipole moment is the vector sum of both the dipole moments of OH bonds. We have two OH bonds, right? One is this bond, one is this bond. Now let's look at some other examples. The dipole moment of BeF2 molecule, right? Dipole moment of BeF2 molecule, beryllium fluoride. It's like this, Be fluorine. Right. Now dipole moment of this molecule, this is fluorine is more electronegative, so this is how we will represent the dipole moment, right? Pointing towards more electronegative. Here also we will point it towards more electronegative, right? Since we said it's a vector quantity and the direction of both the dipole moments is opposite, right, based on how these bonds are arranged, right, in space. So dipole moment also depends on how bonds are arranged in space and the symmetry of the molecule, right? So this is your symmetric molecule, right? This molecule is symmetric, right? So dipole moment due to one bond, right, cancels due to dipole moment due to other bond. So both these bonds, right, cancels the dipole moment of one another. So the dipole moment on this molecule is 0, right? Why? Because the dipole moment due to one bond cancels out the dipole moment of other bond, or what we say is dipole moment of both these bonds cancel each other, right? And this is a symmetric molecule. Now let's look at some other example, right? Now let's take the example of boron trifluoride, right? Let's take the example of boron trifluoride. How will you represent? Fluorine is highly electronegative, right? So it would be like this. This is like this. This is how you will represent, right? This is how you will represent. So net dipole moment is in this direction, right, of boron trifluoride. I'm sorry. This is not correct. We draw it. This is fluorine, right? Here it's more electronegative. It's like this. I'm sorry. Right? So here also dipole moment of these two bonds will cancel out due to this bond. Right? Here again the dipole moment is 0. Right? The BF bonds are oriented at angle of 120 to one another, right? Both these boron BF bonds, right, there is an angle of 120 between, right? So here also dipole moment is 0. Why? Because dipole moment due to these two, if you just draw the vectors, will be cancelled out due to this dipole moment which is in opposite direction, right? If you look at this molecule, here fluorine, here the dipole moment, if you look at this bond, the dipole moment is in this direction, and here dipole moment is in this direction. So dipole moment due to these two bonds will be cancelled out due to this bond. So dipole moment of this molecule is again 0, right? So basically what we are looking at is the dipole moment of one molecule. The dipole moment depends on the arrangement of bonds in space, right? How these bonds are arranged, right? So let's just quickly look at two molecules, right? Ammonia and NF3 molecule. Right? We have a molecule ammonia and NF3 molecule. Ammonia is represented as like this. There is a lone pair here which is represented like this, right? Then you have NF3. Here also you have NF3, right? So here fluorine is more electronegative than hydrogen, but the dipole moment of ammonia is more than that of fluorine. This is what we need to understand, right? Why is the dipole moment of ammonia is more than that of dipole moment of ammonia is greater than the dipole moment of due to of NF3. Why? If you look at the direction, this, right, and this is how you will represent it. If you draw the dipole moments of this, it's like this, it's like this. If you look at the directions, here dipole moment is pointing in this direction, right? This is your lone pair, right? So dipole moment would be in this direction.